Hello and welcome. Today, we're diving into a concept called internal energy. Now, I know what you might be thinking. It sounds a lot like heat, or maybe temperature, right? Well, it turns out it's something fundamentally different and way more interesting. We're going to break down all that hidden energy packed inside everything around us. Let's get right into it.
So, to get our brains warmed up, let's start with a little puzzle. Imagine a single lit match. It's tiny, but it's incredibly hot, right? Now, picture a full bathtub of just warm water. Comfy, but not scorching. The question is, which one has more internal energy? The super hot match or that huge tub of water? Go on, take a guess. Okay, you ready for the answer? It's the bathtub. And yeah, that might seem totally backward at first, but here's why. While that match has a really high temperature, it's got very little mass, not that many molecules. The bathtub, on the other hand, has a lower temperature, sure, but it's packed with trillions upon trillions of water molecules. Internal energy is the total energy of all those particles added together. The sheer number of molecules in that tub means its total energy is just way, way big. So here's our game plan for today. We'll start by getting our definitions straight. Then we'll look at how this energy behaves in solids, liquids, and gases. We'll do a quick Q&A to lock in the ideas, tackle some exam-level problems, and then wrap up with the big picture. First things first, let's get our language right. In physics, words matter, and telling the difference between internal energy, temperature, and heat is absolutely crucial. It's the foundation for everything that comes next. So here it is, the official definition. Internal energy is the sum of the random kinetic and potential energies of all the molecules inside a substance. The two key ideas there are kinetic and potential. You can think of kinetic energy as motion, particles wiggling, sliding around, or zipping through space. And potential energy? That's the stored energy in the bonds between those particles. It's all about how they're arranged and the forces holding them together. I love this analogy because it really clears things up. Think of a country. Its internal energy is like the total wealth of every single citizen combined, all the money in the entire nation. Its temperature is like the average income. It tells you something useful, but it's not the whole story. And heat? Heat is the transfer. It's the money actually moving from a richer person to a poorer one. So you see, an object doesn't have heat. Heat is the energy that flows because of a temperature difference. So it all boils down to this really simple core idea. The internal energy of a thing is just the total kinetic energy of its moving particles, plus the total potential energy stored in the bonds between them. That's it. That's the whole shebang. All right, let's build on that. Now that we've got the what, let's look at the how. How does this internal energy actually play out when something changes state? You know, from a solid to a liquid to a gas. Now, check out this graph. This is super important. In any substance, the molecules aren't all moving at the same speed. It's not that simple. Some are slow, some are crazy fast, and most are somewhere in the middle. Temperature just measures the average speed. But internal energy accounts for every single one. It's the grand total of the energy of all the particles across this whole distribution. Let's follow the journey. Imagine we're heating a block of ice. At first, as we add energy, the water molecules just vibrate faster and faster in place. Their kinetic energy goes up and the temperature rises. But then we hit 0 degrees, the melting point. Suddenly, the temperature stops rising, even though we're still adding energy. Where's it going? It's all being used to break the bonds of the ice crystal, increasing the potential energy. Once it's all liquid, the temperature starts climbing again, until we hit the boiling point. And the same thing happens. The temperature flatlines as all the energy goes into turning that liquid into a gas. So if there's one thing to take away from that, it's this. On a heating graph, whenever you see a line sloping up, that means kinetic energy is rising. The temperature is going up. But whenever you see a flat plateau, that's a phase change. The temperature is stuck, and all that energy is going into increasing potential energy, literally rearranging the substance's molecular structure. Okay, that was the core theory. Let's do a quick fire Q&A round to make sure these ideas are really sinking in. Ready? First one up, and this gets right to the heart of it. Is it possible for the internal energy of something to go up or down, even if a thermometer stuck in it shows no change at all? Absolutely, yes. It happens every time something melts or boils. Think about that ice at 0 degrees. You're pumping energy into it, so its internal energy is definitely increasing. But because all that energy is being hijacked to do one job, break bonds and increase potential energy, the average kinetic energy doesn't budge. And that's what temperature measures. So the temperature stays flat until the phase change is totally done. Okay, next question. What are the big things that control how much internal energy a system has? What factors does it depend on? There are 4 big ones. First, temperature. Hotter means faster particles, so more kinetic energy. Easy enough. Second, state of matter. As we saw, gases have more energy than liquids, and liquids more than solids because of that potential energy difference. Third, mass. This is our bathtub versus matchstick example. More stuff means more energy, period. And finally, the type of substance. Different materials have different kinds of bonds, which means their potential energy is different right from the start. All right, you've totally got the fundamentals down. Now let's level up. Let's see how you can use this knowledge to crack some of those trickier exam-style questions. This is where the rubber meets the road. And to do that, we need to bring in the big guns, the first law of thermodynamics. It's basically a law about conservation of energy. All it says is that you can change a system's internal energy in 2 ways, by adding or removing heat, which is Q, or by doing work on it or letting it do work, which is W. So here's a classic problem. You have a chunk of ice at exactly 0 degrees Celsius. It melts into water, also at exactly 0 degrees. What happened to its internal energy? And more importantly, why? Well, we know its internal energy has to go up. For the ice to melt, it has to absorb heat from its surroundings. That's the Q from our equation. But we also know the temperature didn't change, so the average kinetic energy of the molecules is the same. So where did all that energy go? It was invested entirely in increasing the system's potential energy. It broke the rigid crystal structure of ice and let the molecules move more freely as a liquid. Let's look at another one, this time focusing on the work part of that equation. What happens to the internal energy of the air in a bike pump when you slam the handle down? And what about a simple spring when you stretch it out? In both cases, the internal energy increases. When you compress that gas, you are doing work on it. You're physically ramming those air molecules together, making them collide harder and more often. This directly increases their kinetic energy, and you feel that as the pump getting hot. With the spring, you're also doing work on it by stretching it. That work gets stored as elastic potential energy within the material's molecular bonds, increasing the spring's total internal energy. So we've gone from the basics to phase changes to the first law of thermodynamics. What's the big picture here? It's that internal energy is the true total energy of a system. It's the grand sum of every jiggle, every vibration, and every bond of all its countless atoms. And that leaves us with one final mind-bending thought. If internal energy is all about microscopic motion and stored energy, what happens when you get to the coldest temperature theoretically possible, absolute 0? That's minus 273.15 Celsius. In theory, all that classical particle motion should just stop. They'd be at their minimum possible internal energy. But do they become perfectly still? Well, that's a question that pushes us right into the weird world of quantum mechanics, and it's a perfect cliffhanger to end on. Thanks for joining me.